So, have you ever really stopped to wonder why we're here? I don't mean in some deep philosophical way, but in a purely physical one. Why is our universe the way it is? Why does it have these exact properties that allow for galaxies and stars and planets and, well, us? Turns out our very existence is balanced on an impossibly fine knife's edge. And the multiverse? That might just be the best explanation for why we haven't completely fallen off. Let's just start with a number it's almost impossible to really picture in your head. This number right here represents the insane precision of what's called the cosmological constant. It's basically the energy of empty space. Now, if this number was what physicists actually expected it to be, our universe would have just poof. It would have blown apart so fast that nothing, not even a single atom, could have ever formed. Instead, here we are. We live in a universe that is fine-tuned to 1 part in 10 to 120th power. That is a cosmic lucky number on a scale that is just staggering. You know, the physicist Freeman Dyson, he just captured this mystery perfectly. And here's the kicker. It's not just one lucky number. There are dozens of them. This is what's known as the fine-tuning problem, and it is honestly one of the biggest puzzles in all of physics. It really does feel like the universe was set up just for us. So what on earth is the explanation? To get to the bottom of this, we're going to start with that fine-tuning puzzle itself. Then we're going to climb a kind of ladder of ideas, exploring 3 different types of multiverses: the cosmological, the quantum, and finally, the really mind-bending one, the mathematical universe. We'll wrap it all up by asking the big question: is this all just science, or is it something else entirely? Okay, so first things first. Let's really dig into the core problem that sends physicists looking for other universes to begin with. And that is the sheer, mind-boggling improbability of our own. So anytime you build a mathematical model of a universe, you need 3 key ingredients. You need the laws, right? Things like general relativity that tell you how things change. You need the initial conditions, basically the starting point at the Big Bang. And then you have the fundamental constants. These are just numbers that get plugged into the equations. And this is the strange part. These constants, they're not derived from some deep theory. We just measure them. And that is where our puzzle begins. Let's just look at a few examples, because this is where it gets really wild. We already saw the cosmological constant. Now, think about the Higgs vacuum expectation value, or VEV. It's a number that basically sets the mass for fundamental particles. If it were just a tiny bit larger, all atoms would just fall apart. A little smaller, only neutrons would exist. No chemistry, no life. It is the exact same story for the lumpiness of the early universe. Too smooth and you get no galaxies. Too lumpy and everything just collapses into black holes. It seems like our universe exists in this impossibly tiny, life-permitting sliver of what's actually mathematically possible. So how do you explain this incredible luck? Well, the first step up our ladder of explanations is the idea that maybe our universe isn't the only game in town. There might be others, far, far beyond what we can see. Okay, so this is the most straightforward kind of multiverse. Our best theory for the universe's explosive birth, cosmic inflation, it actually predicts that space is just vast, probably infinite. And if you have an infinite space where matter is just arranged randomly, well, probability alone says there have to be other regions out there that are identical to ours. That means, and this is a wild thought, there is literally another you out there somewhere, simply because there's enough space for every single possibility to play out. Now, let's take that a step further. Inflation was a really violent process, right? It could have created different pocket universes where the actual constants of physics themselves are totally different. I mean, imagine universes where gravity is way stronger or electrons are much heavier. Most of them would be totally sterile, dead. But if there are infinite universes out there, then suddenly it's not so surprising that we happen to find ourselves living in one of the rare ones that actually works. Think of it like this. Imagine a fish that's only ever lived in the warm Caribbean. That fish might assume that water is liquid is some fundamental law of the universe. It would have absolutely no concept of ice or steam. Well, in the same way, we see our one set of physical constants, and we assume they're the only ones possible, when maybe, just maybe, we're in one particular phase of a much, much larger reality. So what this really all means is that some numbers we once thought were absolutely fundamental, like say the mass of a proton, they might not be universal laws at all. They could just be local environmental facts about our neighborhood, kind of like the number of planets in our solar system. That number isn't some deep truth about physics, right? It's just part of our cosmic address in a vast, sprawling multiverse. Okay, let's climb up to the next rung on the ladder. We're gonna go from the unimaginable scale of the cosmos down to the absolutely bizarre world of quantum mechanics, where other universes might be right here in this very room with us. It all comes down to this one seemingly simple question. When a particle is in a superposition of states, it could be here or it could be there at the same time, what actually happens the moment you look at it? The answer to that question splits physicists into two camps and leads to a radically different kind of multiverse.
So, here is the divide. The traditional view, the Copenhagen interpretation, says that the moment you look, nature just sort of randomly picks one outcome, and all the other possibilities, they just vanish, gone. But the many worlds interpretation has a much wilder idea. It says nothing vanishes. Instead, reality itself splits. The universe branches into all these parallel streams, one where the particle was here and a whole other one where the particle was there.
This is the level 3 multiverse. And get this, it's not far away in space. It's happening constantly, every second, all around us. And from our perspective, since we're trapped inside just one of these branches, this constant splitting just feels, it feels like a random outcome. The physicist Hugh Everett argued that what we call randomness is simply the subjective experience of our own consciousness being cloned across multiple new worlds. Yeah, wild. All right, you might want to prepare yourself for this one because we have officially reached the top of the ladder. This is by far the most speculative, the most abstract, and honestly, the most profound multiverse of them all. Stephen Hawking posed the ultimate question here. Physics tells us that our universe is described beautifully by a very specific set of mathematical equations. But there are countless other possible mathematical structures out there. So why this one? What makes our particular set of equations so special that it gets to be physically real? The level 4 multiverse offers a pretty radical answer. Nothing. It's not special at all. This idea proposes that physical existence and mathematical existence are the exact same thing. Every single mathematical structure that is self-consistent, from simple geometry to bizarre alien physics we can't even imagine, it exists as its own universe. Our universe isn't special. It just happens to be one of the ones that's complex enough to allow for consciousness to emerge and sort of observe it from the inside. And this brings a kind of ultimate simplicity to the whole idea. A theory of everything t-shirt for those other multiverses would need all these complex equations written on it. But for the level 4 multiverse, the t-shirt would just be blank, completely blank. You don't need to write down any specific equations because all possible mathematical structures simply are. Okay, wow, we have climbed the ladder of speculation. So now it's time to come back down to earth a little bit and ask the really important question. How should we think about these absolutely incredible ideas? When you really get down to it, when you want to explain the fine-tuning of our universe, there are really 3 main contenders on the table. You've got theism, which suggests a purposeful designer set it all up. You've got the multiverse, which suggests a kind of cosmic lottery. We're here simply because we're in one of the few places where we could be. And then there are some forms of pantheism, which propose that the universe itself is a kind of divine consciousness, working within its own limitations. Now, this is the big objection, right? This is where a lot of people pump the brakes. If we can never, ever see these other universes, how can the multiverse possibly be a scientific theory? Isn't it just as much a leap of faith as any other explanation? Well, the defense is at the line between what's science and what isn't. It's not quite as simple as can you test it. Scientists also judge theories on things like their simplicity, their explanatory power, and this is key, whether they just naturally fall out of our best tested models, like inflation and quantum mechanics. So while the multiverse is really hard to test directly, it is a natural consequence of theories we already have very good reason to trust. And that leaves us with one final, truly dizzying thought to ponder. If that level 4 multiverse is real, if our entire reality is just one of countless mathematical structures that simply exist, what does that mean for us? It kind of suggests that we and everything we can possibly imagine, we weren't really created or invented. We were inevitable. We were simply discovered, like a mathematician finding a new shape that was always out there, just waiting. So, what do you think?